How are we doing, everybody? Happy New Year! Hope everybody had a good time. Hope everybody was safe and responsible, because that's what it's supposed to be. You're not supposed to do anything you're supposed to regret for this whole entire new year. Hold on one second. The wife's texting me. All right. So yeah, Happy New Year, everybody. We got the night off, so we got to go a little bit into the late hour tonight. We will. Let me pull up my chat. The wife's telling me, look at your chat. I'm getting to it. We will. Hello. Here's a hug. He's so bad at that. All right. How'd you like my intro, honey? Did you like it? Ah. So it's pizza for dinner. You are not cooking. LOL. Pizza for dinner. Everybody loves a pizza, right? It was sexy bee. I thought I'd give it like the old 90s MTV type look to it this afternoon. All right. So I love you, baby. It's so good. Mwah. So Just trying to scarf down some of my morning oatmeals. Mm. Might not be your morning, but surely is mine. Alright. Like I said, we're jumping right back into where we left off. I got Cisco Packet Tracer up today. Text me some halabula. Halabula! Halabula bula blah blah. Text me some halabula blah. I'm speaking your language, ain't I, baby? Alright. Without further ado, ladies and gents, I guess let's just dive right into it, right? That's just what it's about. Alright. Well, like I said, I got a packet tracer up right now. I'm we're gonna be in Cisco Packet Tracer instead of Cisco Modeling Lab today, just so it's not so processor heavy on uh-oh. What did you do? What did you spam? Oh, my Nightbot gotcha. My Nightbot gotcha. Well, you can't do any emotes at all? What the hell happened? Dude, it just deleted all of your messages. Actually, I need to know like what you did because I can't even see what you did now because you just deleted everything you just did. Hold on, let me log into him. I knew I had my Nightbot set up pretty strict. I see what you did. But I can't believe he deleted all of your messages like that. I'll have to loosen him up a little bit. Oh, so he's set to a limit of 3 emotes. Yeah, I'll set it to a limit of... I'm gonna set him to 10. Alright, I'll set him to 10. Alright, now try to do a couple emotes now. Don't do more than 10 though. There you go. There you go, baby. No more than 10 emotes. I loosened them up a little bit on you. That was funny. The first person who got ripped up by my netbot was my wife. It timed you out again? How many? I got my nightbot set up pretty strict. That's funny. You just messed me up. Now I'm over here trying to fix this thing. All right, I'm gonna have to put some work into him. When you come home, we'll work on. He's mad at me now. No, I see. Trust me, I see what I see. I see what he did to you. But he allowed the other emos to go through. Oh, what is he doing? All right, we'll have to work on the nightbot when you get back home. My bad, honey bunnies. Where's the way? Oh shoot, it timed you out for a while too. How do I undo that? Huh. Damn, 600 seconds. That's pretty hardcore there, Nightbot. Just pretty much kicked my wife out of the chat. So I'm gonna set you to. How do I set that? Accept user precision. On. Maybe I'm gonna disable him for now. See if you can come back in the chat now, babe. I just disabled him. Yeah, that thing is pretty ruthless. Mm-hmm. How do I, I'll have to do... Alright, I'm gonna have to work on that one. Alright, more to come on that one. Sorry, baby. Alright. Let's go. Let's get to studying, everybody. Now that I'm completely distracted. Alright. How's everybody doing? See if you can chat now. Or if it's still... I disabled it. Oh, alright. Alright, baby. Alright. Let's get to it, everybody. Sorry about that distraction. Mr. Nightbot took it out on my wife today. I didn't realize how strict I had it set, I guess. And she was just trying to rub a couple of emotes, and he pretty much just kicked it totally out of my ring. My stream. Alright. So yesterday we ended off about midway through chapter 16. We were getting into packets and how when the frame enters into a router, what does that router do to that frame? So what I thought would be a nice idea today was to jump over to Packet Tracer, because again, Packet Tracer is a little bit lighter of a program than Cisco Model and Lab, and there's just a couple little caveats that I could do in Packet Tracer that, you know, per se. Oh, there we go. Huh? Yeah, I disabled him. Sorry about that. So yeah, there's just some caveats to Cisco Packet Tracer than there are to Cisco Model Net per se. Nothing to take away from either one of them, but I thought it'd just be nicer to do that today for you guys. I also fixed my Windows VM. I love you too, baby. Fixed the Windows VM today too. So, all right. So here, we'll drop a router into our topology here, and let's take a look. Let's take a look at the actual router and see what. So this right here, this is a which one is this one again? I think this was the 40. The 4331. So that's the 4331. And what you're seeing here now if we remember when we were talking about oh, there you go. So this right here, this area, let me get an actual router that maybe the 1941. No, I guess that wouldn't be. Or the 2811. More like a. Yeah. I like that packet tracer router. So, all right. Oh, okay. All right. Yeah. So let's just use. Let's use this router as a for instance. I have a couple serial links, right? We ain't gonna be using those. We ain't gonna be using these, these, these. But those they don't like to move that. All right, so I'm just gonna add a couple Ethernet lines to this thing, gigabit Ethernet lines. I'm probably gonna add. I'm gonna add a little bit. Yeah, be excessive with it. That's cool. Turn it on. All right, so what you're seeing. So obviously we have our console, a console line. That's what we would be using generally to log into the router, physically log into the router. You know what I'm saying? Well, trying to do too many things at once. There's too many things in my head. All right. Now we have the auxiliary. That's if we were using it to log into the router via like a phone line. All right, and that's what was explained in chapter 15 there. All right. All right, and then we have our gigabit Ethernet ports, serial port, all right, and then a line port, all right. Stop fresh real quick. There we go. A nice empty one. I like that. Okay. So, what is this? A couple of gigabit Ethernet lines? Okay. Yep, gotta turn it off. Let's start with our nice fresh packet tracer router here. All right. Let's come over here. Is this a serial? Let's add our serial line first. Then let's add some gigabit Ethernet, okay? Let's add one more. All right. Power that back up. Minimize that down. Zoom out. Exit down. Come over here. Do the same thing to this one. Grab that serial line again. Grab some gigabit Ethernets. All right. We'll grab a couple of these routers here. Make a connection. Let's go serial. Let's get that going. So we have a serial line going from there to there. Back. Grab another couple of routers. These ones. Give these a couple of gigabit Ethernet interfaces, and that should be good enough. Again, I didn't power it on, did I? Nope. Power it on. All right, so we just created a quick topology, sort of, kind of. Let's make some links. Switch. Say we'll grab the packet tracer switchy switch. Up real quick. Gigabit Ethernets. Add on. You know what I should have done? I should have just done. I want to start empty with everything. That's fine. Start everything empty, man. There we go. That's what I want. Empty. Few gigabits. Power on. Next one. What was your? Oh, we gotta turn it off first. I'm always forgetting to turn these guys off. Get that started. Fill it up. I like Cisco packages. It's so neat. So cool that you get to do this and look at it. So I tell everybody, there's something great, there is something great about Cisco packet trace. I would never take anything away from what it is. You know what I'm saying? It's such a great program. Done. All right. All right. So we got some routers. We got some switches. All right. We're gonna create a cool topology here. All right, to illustrate just some routing. You know, you don't need any hubby hubs. The only hub you need is me, the hubby of the hubs. It's a coaxial splitter though. Security devices. Ooh, there's some DLC modems. Makes me think. Takes me, I think. Almost on now, man. Man, I guess we won't get into any of that hoopity. But I guess though, yeah, let's do that. Let's make one the server farm, right? Yeah, that's fine. Put pieces over here. Pieces over here. And then maybe a couple of servers over here. All right. We'll worry about labeling and all that here shortly. Sort of, kind of, yeah. I'm down with that for now. That's cool for now. That's cool for now, so. Alright. Let's just finish making some connections real quick. That's good, you know. Good enough for this for now. We'll just let that marinate for a second or two. Alright. Whoa, lost me mouse. Alright. Well, that's marinating. Let's get back to the chapter review. Yeah, let's get back to the chapter real quick and we'll review it. Touch just on a couple things. Like I said, we were talking about how what that packet is doing. Trying to just get all my, so I can see all these. No. Have it. Let me get that you. Okay. Alright. Good enough. Now I can actually see all the interfaces and everything. That's all I was trying to do. Alright. Alright, so like we were discussing how um when a frame enters into a router, it de-encapsulates that frame and takes a look at that IP packet that's sitting inside that Ethernet frame, that Ethernet header and trailer. Now, depending on what the information inside of that IP packet is saying, it makes a couple of decisions. It either drops it because it doesn't, there's nowhere for it to route it. So when it de-encapsulates that, at least from what this is stating, it first runs through the frame check sequence to make sure that the MAC address, the MAC address was supposed to go to that router. So that frame was supposed to go to that router. If that frame check passes the frame check sequence, that router figures out that this Ethernet frame was meant for itself. Then it de-encapsulates that IP packet out of that Ethernet trailer and header, and then takes a look at that information inside of that IP packet. And then what it does with that IP packet, it takes it takes a look at the destination IP address and takes a look at its actual routing table, and then it makes a couple more decisions. It says, okay, do I know where to route this packet? Do I have a interface that I could send this packet out of to be routable? Or is this, like, say, is this packet going to a network that I'm sitting on to? If not, do I have a default gateway that I can send this packet to? And then if not, then I'm dropping this packet. But if I have a default gateway that states that I can send this packet to another, maybe another router, then I'll send this packet off to another router. So then that router can then make a decision where to send this packet off from there. All right. Again, it makes a couple choices. It makes a couple decisions. The routers do this. So there's some processing. There's some processes that these routers are actually doing to make smart decisions. Okay. That's why a router is a router. It's making smart decisions on what to do with these Ethernet frames, okay? Because it's got to deal with these IP packets that are encapsulated inside of these Ethernet frames, okay? It's not like a layer 2 switch that just gets these frames and says, okay, I'm getting this frame from this source. The source resides off of 501, all right, and the destination is matching a MAC address off of my my 502 port, so I'm just gonna send it out there. Or if I don't know where the destination is, I'm just gonna flood it out all my ports, and maybe maybe the person it's intended for will get it. Well, routers make smart forwarding decisions. If they have, say they get that packet says, I'm going to somewhere within our actual local network. That router is going to say, okay, I have an IP address now, and I know where to send it. It's somewhere in my network, but I don't know where that MAC address is. I don't know what that MAC address is for that actual device. So let me send out an ARP request first out to everybody, out on this that it's sending it through the broadcast, the FFF. That's the address it's going to send it out of. So it's like a multicast address, all right. And then that's going to send the ARP messages out, and then whoever has that IP address that router is looking for, it's going to send its layer 2 information back to that router, and then that router is going to encapsulate it in. It's going to encapsulate a new Ethernet header and trailer frame All right, but it's also going to maintain that IP packet, so it's going to put that IP packet back into a new Ethernet header and trailer, and then forward that Ethernet header and trailer back out. All right. Um, so it's a process of de-encapsulating the data that it gets, and then re-encapsulating the data that it's getting. All right. Um, Let me just finish my one more bite. Oh, it's so cold. Ugh. All right. All right. So we'll I guess start off back at the at step one. I think I turned that heat down too much, but it's fine. It's funny. It was like scalding and hot in his house when I got out not too long ago, and now I turned it down just like 5 degrees, and now it's freezing. All right. Routing step one: deciding whether to process the incoming frame. Routers receive many frames in an interface, particularly local area network interfaces. However, a router can and should ignore some of those frames. So the first step in the routing process begins with the decision whether a router should process the frame or slightly disregard or ignore the frame. First, the router does a simple but important check, step 1A, in the process summary, so that the router ignores all frames that had bit errors during the transmissions. Routers use the data link trailer failed check sequence failed to check the frame, and if errors occur in transmission, the routers discard the frame. The routers make no attempt at error recovery. That is, the routers do not ask to the sender to retransmit the data. The routers also check the destination data link address in step B to decide whether the frame is intended for the router. For example, the frame sent to the router's unicast MAC address for the interface are clearly sent to that router. However, a router can actually receive a frame sent to other unicast MAC addresses, and routers should ignore those frames. So it's just saying when that router, like exactly what I just said earlier, when that router receives that frame, it processes it through a failed check sequence. So it takes a look at it first, makes a decision: is this meant for me? All right, is this unicast address, is this my MAC address? If this is not my MAC address, then I don't have to go through all my other processes, because I've already identified that this frame that I just got in either has errors in it and then I'm not dealing with it, or this wasn't even intended for me in the first place, so I'm just going to drop it. So a router makes a couple decisions, mainly one. It goes through at least a process. I want to say it's the decision. It just goes through a process. Determining that process then determines a decision. Okay, all right, and that decision is either do I then continue on processing this and then making more decisions after that, or do I just make the decision now to just drop it and then not deal with it at all, and not waste any more processing power that I don't need to deal with, because I'm probably dealing with there's other Ethernet frames that are coming in probably at the same time, and maybe one of those is destined for me and is a Ethernet frame that I should be dealing with and then processing, de-encapsulating, encapsulating. So that's the first thought process of how a router is starting to do its job. Okay. All right. For example, routers will receive some unicast frames sent to all other devices in the VLAN, just because of how LAN switches work. Think back to how LAN switches forward unknown unicast frames for which the switch does not for which the switch does not list the destination MAC address in the MAC address table. The LAN switch floods those frames. So again, when a switch gets a Ethernet frame, okay, and it doesn't know particularly where to send this frame, it's gonna say, okay, well, I'm just gonna flood it out to everybody, and hopefully the person that it's intended for gets it. If not, and it's okay with me, I don't care. So that's layer 2 type logic, okay? All right, and what's going to happen is your router with that's sitting inside of that VLAN is going to be just is going to be bombarded with those flooded frames, okay? All right. The result. Routers sometimes receive frames destined for some other devices with some other device MAC addresses listed as the destination MAC address. Router should ignore those frames. Okay. In this example, host A sends a frame destined for R1's MAC address. So after the frame is received and R1 confirms that the fail check sequence had no errors, R1 confirms that the frame is destined for R1's MAC address, the 0.2.0.0, yep. In this case, all checks pass, so the router will process the frame. Note that large. So this is just depicting how this is just pretty much depicting like the inside workings of an actual router. So you have the interface right here, the Ethernet frame. Here's the IP packet that's encapsulated inside of that Ethernet header and trailer here. These are just some ports. So we have a serial port 001, 000, and then we have a serial port 0-0-01. All right. Now it states that the MAC address right here is my MAC address. Is this my MAC address? Okay, it is my MAC address. All right. So this is a frame that I'm supposed to be dealing with. Okay. All right. De-encapsulating the IP packet after the router knows that. What am I doing over? After the router knows that it ought to process. Man, I swear, some of these chapters in here are written. I don't know if it's just how I'm reading it or it's just how it's written. It's so difficult sometimes for me to read it. Some of these chapters in here, it's like the words just do not flow good. All right. Might be on purpose. All right. After the router knows that it ought to process the receiving frame, the next step is relatively simple. De-encapsulate the packet in router memory. The routers no longer need the original frame's data link header and trailer. So the router removes and discards them, leaving the IP packet as shown. All right, again, so it rips out the IP packet. That's not what I want to do. It rips that IP packet out of that Ethernet header and trailer, and then disregards that IP pack it disregards that Ethernet header and trailer. It says, I don't need you no more. See you later. All right, because what's going to happen is that router is going to re-encapsulate that IP packet in a new Ethernet header and trailer, okay? So it's going to take the old Ethernet header and trailer. It's going to remove it's going to de-encapsulate that IP packet out of it. It's going to just get rid of that other Ethernet header trailer information, all right? And then it's going to re-encapsulate that IP packet into a new header and trailer, okay? That's why you see. Man, it's going to be push-up time here soon. I'm telling you guys. Telling you. If I keep up this yawning booty crap. It's like I wake up when time I'm supposed to be waking up and I'm still super tired. I don't get it. I'm supposed to be focusing on studying here, not yawning. I get aggravated with myself when I do that. I'm telling you, like these last couple of days, it's just been rough. It's been like actually, it's been the last 2 weeks ever since I started working the overnight. It's like I just cannot get right anymore. But I guess that's part of working overnight. You ain't right anymore. All right. Especially I've never done it in my life. So, yep. So, again, removes and discards, leaving the IP packet shown. Note that the destination IP address remains unchanged. So, again, it does not, that's one thing we have to remember. It does not change that IP packet, okay? It's leaving that IP packet alone, all right? The only thing it's dealing with, the only thing it's destroying and remaking is the Ethernet header and trailer. It's not so much it's destroying, it's just plucking the information out of the one that it received it on, and then making a whole new one, okay? I guess you can call it destroying, because it doesn't do anything with it. It just goes, see you later, alligator. But that IP packet will be, it will be left alone. It's just because it's going to do something else with that. It's going to put it back in a new box. Okay. All right. Step 3. Oh. All right. While routing step 2 required little thought, step 3 requires a little bit more thought on all the steps. At this point, the router needs to make a choice about whether to forward the packet, where to forward the packet next. The process uses the router's IP routing table with some matching logic to compare the packet destination address to the table. First, an IP routing table lists all multiple zones, multiple routes. Each route contains several facts, which in turn can be grouped as shown. Part of each route is used to match the destination address of the packet. Part of the destination address of the packet, while the rest of the route lists forwarding instructions where to send the packet. Okay, so what that pretty much is okay. We have our subnets. These are the masks. Do we have an X router? Out of what interface? Okay. All right. You know what? We're gonna have to do some push-ups, guys. I'm gonna get mad at myself. So let's do some push-ups real quick so we can wake up here. Push-up cam. Push-up cam, guys. Push-up cam time. Hoo-ah! All right, here we go. Let's do some 10 just to get warmed up real quick. Ooh, stretch out. My stream's gonna turn into it's gonna turn into a physical exercise stream next too, guys. Watch. Ready? Oh. 1, 2, 3, 4, 5. There you go. 6, 7, 8, 9, 10. There you go. Getting started off. All right. All right. Let's get back. Let me grab a seltzer water real quick, guys. Need to wake up. All right. So here we go. Here's some of its logic in a very nice way. All right. So we have our address, okay? So what that address is telling us, there's some information in this address that we should look at. Okay? 172.16.2. All right. Now let's get back to subnetting dots. Okay. What we're looking for that network. Okay. We're not so much right now. We want to find the network. Okay. So in that router is going to do the same thing. Okay. And that's pretty much what this illustration is telling us is okay. Where's that network inside of this address? Do we have what's our mask? So it identified the mask as being a /24 mask, which again, a /24 puts the network octets. It's inside of the first 3 octets of that address. So 172.16.2 would be the network. Okay, so we're gonna take a look at our routing table. We got 16.1, 16.2, 16.3, 16.4, 16.5. Okay. So we found a network that matches the network in that IP packet. So we have a matching network, okay? So we know it, okay? Now, let's take a look at our next hops. We have to look at our hops here. Well, that's what this is at least stating. All right? It's stating that to get this packet to the 172.16.2 network, we have to send this packet to the 172.16.4.2 router. So there's a router somewhere in this topology somewhere that has routes to other networks. And on this router's routing table, it's the 172.16.4.2. There's that router out there that can get this packet to the 172.16.2 network, okay? All right? And then it says, okay, what interface do I have to send this then to get to that the 172.16.4.2 router? Okay, it's out of my serial 0-0 interface, okay, that I'm going to be sending it to so that packet then continues get forward out, okay? So out of this, let me kind of jack that up a little bit. So out of my serial -0-0-0 port, I can send that packet now out, and it's not going to be my bag of problems afterwards, but it's going to be going to another router. And that router is going to be doing a similar process from here. Okay. All right. Continue on. Focus on the entire routing table for a moment, and notice the facts. We're going to be doing more push-ups, Joe, if you keep yawning. No. Focus on the entire routing table for a moment, and notice the facts that is listed. Notice the facts that it lists 5 routes. Notice the facts that it lists 5 routes. Okay. Earlier shown the entire example, 5 subnets. So R1 has routes for each of the 5 subnets. Next, look at the part in the 5 routes that R1 will use to match packets. To finally define each subnet, each route lists the subnet's IDs and the subnet mask when matching the IP packet's destination and routing table. The routers look at the packet destination address. Give me 1 second. Be right back. Hold on 1 second. All right. Sorry about that, guys. Okay. All right. Need to refocus and regroup. All right. Let's continue on. All right. Let's take a look back at that diagram. And you know what? I'll do. I'll save this. What we got? We got one, two. We got a couple statics. Let's make this topology, you guys. Cloud is representing. I can use just this little serial link. It's fine. But we built their topology just like how they have it, and this description. And let's make. Oh, my stomach's getting bad. Um. Oh, okay. So that's actually representing Ethernet. make let's make this addressing just like they have it here. So it'd be 172's 172's. Hurry up and boot up. Good. What's that? Can you guys see that? Go down to that should be enough. We'll have to switch back and forth when I go to the other routers, but this is good for now. All right, so which router are we actually at right now? That router. What was that router's? So that has an interface to 172. Mm-hmm.
And the pizza gonna be here.
Mm-hmm.
And the pizza gonna be here.
I don't order it yet. What's up, buddy?
What's up?
How are you?
What up, fellow streamers?
What's up, fellow streamers?
So I'm going on Fortnite. So is pizza here yet?
No.
Not yet.
Mm.
You didn't order it. Oh.
Alright, so we're gonna go 172, 174, 7. Okay. Base. Hey, honey. Say hi.
What's up? Tired. Not for you.
Huh?
You want it on my card or yours?
Huh? It's up to you, honey. I don't care. Distraction time now. So there's 9. That one is, I'm gonna say IP address. 7216.4.1. So that's what it's the planets, right? Say 2 for 5, 2 for 5, 2 for 5, that's 0. Shut. That one is good. Interface. Address. Oh, dash 0. 2, 16.5.1, 5.0. Yeah. Why did that other interface not come up? Oh wait, I just messed that up, didn't I? I did just mess that up, huh? Alright.
Hello. Hello.
2, 16, 2.5, 2.5.
Wait, maybe the ones who are in the same, we should call them coders. My real friend are coders. Yes. But I did like what you did.
Fireworks.
Also try to when mommy's going to text me. Fireworks. And there's 6, no, 9 of you. There's 9 of you.
9 of what?
9 of your face.
Oh, do you like that?
Yeah. I put 9 in my face here. 9 times the magnet.
No, I'm good. Yeah. Yeah, that's fine. Olives and pepperoni is fine then. Distraction time. Let's not get distracted. Focus. I still gotta figure out why this serial port is still down. Okay. Let's take a quick look at this configuration real quick before we move on to the other routers. this now. It's the same numbers, right? Yep. This. But now.
My card, baby.
You could use mine.
Hmm?
So you could use mine if you
No.
wanted to.
Got it. On me. You can do that now.
You can do that now.
I'm gonna close your door, okay? You're gonna play some recording now.
What does that have the address as? .3. And 3.3. Okay. Interface, loop back. 0. The address 1.3. 2.5. Adjacency. Go. Okay. Exit. CD. I think we have it matched up to theirs now. Wish all be good. Do show routes. And go. Well, we have successfully set the hold. So we got it working. All right, that's cool. Now let's take a look now. Let's take a look at when we send. Let's go back to the illustration. I need to get you guys back out of Zoom mode. Okay. All right. All right. So where are we saying this? So we're stating that PCA, this is PCA. PCB, PCB, that's 1, 2. So similar to how they had theirs set up. No, I should have done is I should have done this. Let's do it. IP, DHCP, exclude addresses 172, 0 through 172. I just wanted to have it the same exact addressing as everything else did. Okay. That way we can see it exactly how they did it. Okay. All right. Now, what was it pinging? It was pinging 72.9, so it's pinging. So PCA is going to ping PCB. So let's go to simulate. let's go to here, desktop. All right, let's go to ping 172.16.2.9. Let me actually, before we do all that, let me go to filters. And just remove a whole bunch of these guys. All right, so we're going to start here where PCA is going to ping PCB. All right. So, what you're seeing already is this ARP. You can already see the ARP message that's about to head out first. Okay. And let's take a look at that. So we can already see here. So the Ethernet header, it's that multicast address, the FFFFFFFFFFF. Okay. Now, its source IP. Its source IP is obviously the actual PC 172.16.1.9. The dash IP is the actual its router. Okay. Here's a look at the actual BDU of it right here. All right, it's sending out that ARP first because it needs to find out the layer 2 information about the actual the router. It doesn't have its layer 2 information just yet. Okay, so once it gets here, so here it is. The FFFFFF, the source came from there. Dashed. Okay. All right. All right. Let's take it to the next step. So it looks like we got the ICMP back. Okay. Pretty much, it's telling it. It's the router's telling it. It's layer 2 information at this point. All right. Let's take a look at this ICMP message. All right. Now this is the. All right. So did you see? We went through 1, 2, 3, 4, 5 messages. 5 messages in total. All right. There was actually 5 messages that went through the wire before our actual ICMP message, our ping message to the to PCB. Okay. So our address resolution protocol, we had to find out first the layer 2 information about our router. Okay. All right. Now here we go. Let's take a look at the. Let me get rid of that. Back to this, and this is what I'm looking at. Okay. All right. So in the layers. So here we are. This is the ICMP message. Actually, let's take a look at the. No, let's take a look at this one. So we have the ICMP message in its layers. So we have the source IP as PCA. Destination is 172.16.2.9 PCB. Okay. It's in an Ethernet header in trailer. So and then now what it's going to do now is again, it's still remaining that. Now it's going to be put inside of so this is Ethernet, since it's traveling through Ethernet, okay? So we're traveling through Ethernet, so Ethernet wiring, okay? Now, since we got to travel through a serial port, that router is going to put that into a HDLC, a high data layer control frame, high data layer control frame, okay? So it's going to wrap that into a high data layer control Ethernet, high data layer Ethernet header and trailer, okay? All right. All right. But look what it just did down, though. All right. It actually set out an ARP. All right. So the Ethernet, so the actual router, all right, send out an actual ARP, all right, to find out layer 2 information, all right, probably about that other router. And then this router just send an ARP request over to the PC, again, to find out layer 2 information, okay? So our ICMP message hasn't even gotten this far yet, okay? Now the PCB is sending back layer 2 information back to that router, okay? Here's some OSPF stuff. I should have removed the OSPF stuff. These are just some of the OSPF's hellos. Just updating, just making sure that everything in the network's still updated. No routes have changed. Check out OSPF. Alright, sorry, I just removed the OSPF, guys. Okay. So now we're back. We're back at PCA, okay? And if we remember, let's go back a couple steps. So we got some ICMP messages. All right, look at that. When this ICMP message from R1 to R2 went there, it was actually dropped. R2's dropping it right there. All right, because again, it doesn't have it's looking for layer 2. Oh man, that came fast. Deliveries. Thank you, baby.
You're welcome.
Mwah.
Didn't catch on camera.
PDA. Oh boy, I'm so embarrassed. I kissed my wife. So it's looking for layer 2 information, okay? All right. Now here we go. So here's going to be another ICMP message, okay? So source IP PCA, destination IP PCB, okay? Now we have some Ethernet, we have some layer 2 information now populated now, okay? Because we've done some of our ARPs, okay? It goes to R1 now. All right. Again, source, PCA, dest, PCB. Again, here's that layer 3 information. It's remaining the same. Okay. But the layer 2 information is being de-encapsulated and then re-encapsulated. Okay. So let me just see what this says. So the gigabit Ethernet 0-1 receives the frame. The frame's destination MAC address matches the receiving port MAC address, broadcast address, or the multicast. The device de-encapsulates the PDU from the Ethernet frame. The device looks up the destination IP address in the routing table. The routing table finds a routing entry to the destination IP address. The destination network can be reached by, okay, same thing so exactly what this is stating here. Okay? All right, so look at that, guys. We created this identically. All right, the destination network can be reached via 172.16.4.2. So exactly how this is description, this is, all right, the network can be reached out of 172.16.2. Okay? All right. All right. Next, the device encapsulates the packet into a HDLC frame. Okay. All right. Now let's read on here, since we're about this far into our reading now. All right. Early in the figure shows the example of private networks. Yep. Next, look at the part of the 5 routes to be point-defined subnet. Each route lists both the subnet ID and the subnet mask. When matching the IP packet's destination with the routing table, the routers look at the packet destination 172.16.2.9 and compares it to the range of addresses defined by each subnet. Specifically, the router looks at the subnet and mask information with a little math. The routers can figure out in the figure of these subnets 172.16.2.9 resides. The route for that subnet obviously is 172.16.2.0. Now remember, when we configured OSPF dynamically learned all of that because once we enabled OSPF on all the routers, they started advertising their actual routes. Okay, so what we did is we told OSPF, we told the routers to start advertising their routes via OSPF messages, and so so I removed the OSPF messages, but you saw those hello messages. That was OSPF just checking out the network to make sure everything was still connected, and still, well, it was just progressively updating the network information. So if we had changed something in the network, or if something went down in the network, OSPF would then dynamically, it'd be able to configure the network, so we'd be able to continue on routing packets if there was an alternate route to route the packets. Guys, give me one more second. I just gotta run the bathroom again. My stomach, but I didn't want the pizza. My stomach's a hot mess today. Hold on, guys. Nice.
Samurai sword on my back. You don't know how to act. Maybe you should relax. Maybe you should relapse. Just kidding.
All right, guys, I'm back. I'm sorry about that. My apologies. Hurting today. Hurting bird. I'm a hurting unit today. All right. Now we're going to continue on. All right. Focus on the entire routing. Yes, we talked about that. Yep. Finally, look at the right side of the figure to the forwarding instructions for the 5 routers. After the route matches the specific route, the route forwards it the information, and the route tells the router where to send the packet next. In this case, the router matches the match to the route for the subnet and forwards it out the serial port. All right. Note, routes for remote subnets typically list both an outgoing interface and next hop router IP address. For routes for subnets that connect directly to the route, list only the outgoing interface because the packet destinations do not need to be sent to another router. Okay. All right. So step 4, encapsulating the packet in the new frame. At this point, the router knows how it will forward the packet. However, the router cannot forward a packet without first wrapping a data link header and trailer around it. Encapsulation. All right. Encapsulating packet for serial links does not require a lot of thought, but in the current CCNA 200-300 exam does not. But the current, yes. I tell you again, the way it's written sometimes, it's like I cannot read it. Encapsulating packets for serial links does not require a lot of thought, but for the current CCNA 200-301 exam, does not require a lot from us. Sure. Okay. Point-to-point serial WAN links use either HDLC, the default, or PPP as the data link protocol. However, we can ignore any data link logic, even ignoring data link addressing, because serial links have only 2 devices on the links: the sender and then the obvious receiver. The data link addressing does not matter. An example, R1 forwards the packet out 0.0.0.0 after encapsulating the packet inside the HDLC frame. Okay, so again, here's the IP packet. Okay, it's remaining the same. Okay, for the destination. All right, there's the IP packet. Now we're just putting it into its own a new high data level control, HDLC. I gotta look that up again. I want to know that exactly what it is. All right, HDLC, high level data link control. High level data link control. Okay, so even though it's HDLC, it's high level instead of HLDLC. I guess that would have just not rolled off the tongue any easier. But it's high level data link control. It's a bit oriented synchronous data link layer protocol developed by the International Organization of Standardization, so the ISO. Okay, all right. That's coming right from the text. Okay, guys. All right. Now let's go back to Packet Tracer and just see that this is exactly what Packet Tracer did too as well. So again, the device encapsulated the packet in HDLC, a high-level data link control frame. Okay, and then it sends it out, the serial 0-0 interface. Okay, and that's all the information that ICMP message has right there for us. Okay, all right, routing step 4 on routing, encapsulating the packet. Note that with some other types of data link, the routers has a little bit more work to do due to at this routing step. For example, sometimes a router forwards a packet out an Ethernet interface. To encapsulate the IP packet, the router needs to build an Ethernet header and an Ethernet, and that Ethernet header destination's MAC address would need to list correct values. For example, consider the packet sent to sent by the same PCA, but with the destination of PC. All right, so let's do this then. Let's finish this. Let's finish this scenario up. Okay. So this was the packet. This was it going from router 1 to router 2 now. Okay. All right. All right. Now you can see when R2 gets it, R2 is de-encapsulating it. Okay. All right. The device de-encapsulates the payload from the HDL frame sent to its upper levels. The device looks at the destination in the routing table. The router finds the routing entry to the destination IP address. The destination network is directly connected. The device sends the destination as the next hop. The device the next hop IP address is a unicast. The ARP process looks up in its ARP table. The next hop IP address in the ARP table, the ARP process sends the frame destination MAC address to the one found in the table. The device encapsulates the PDU into an Ethernet frame now, because now it's sending it via Ethernet. Okay. All right, and it's sending it out its gigabit 1.0. All right, and then it finally reaches its destination. So here we go. It's got to its destination now. All right. Source. Yep. Yep. Cool. All right. -3. All right. Now this is going to be the PCB now. The frame's destination MAC address. Yep. All right, next step. All right. So again, this was the frame that PCB is now sending back to PCA, okay? But it's going to send it back to to router 2 now. Router 2 receives the frame, okay? Just like it did back in the other steps, okay? And then again, it takes a look at it, de-encapsulates it, looks at its routing table, figures out that it needs to sending out its port there, all right, to 172.16.4.1, all right, but it's wrapping that again back into a high-level data link control frame, okay. All right, ICMP now goes to R1. And then finally, PCA receives their first ICMP reply back, okay? All right. So now, after all these messages, PCA finally got their first reply back. That's why when you see, like when you do a ping, if you haven't pinged something just yet, like say, you just all the devices have been off in the network and nothing has no ARP tables or anything like that have been dynamically formatted yet or alert yet. That's why you might the first couple ping, like the first 1 or 2 pings might fail because the address resolution protocol has to do some work to make sure they're finding all the layer 2 information for whatever addresses that you're trying to ping. All right. but then once everything is populated and everything else, again, then these ICMP messages should go off without a problem. As you can see now, we have ICMP messages going back and forth, all right, without issue, okay? All right. All right, so we'll stop that one. We'll start a new simulation. Now let's do this. Read on that, right? All right. So now, here we go. We're gonna be pinging 3.9. Okay. Again, we got to send it over to. So here we go. So, yeah, we'll back up a message. All right, source, obviously PCA, destination, PCC now. Okay, here we go. It's on an Ethernet header and trailer. All right. All right. So the incoming PDU, obviously with the source address as PCA, the destination as PCB. We have some layer 2 information. All right, and then on the outgoing, again, it's continuing to save that IP packet. Doesn't touch that IP packet, okay? But you can see here, all right, so this is the, that's awful. This here is the MAC address for router 1, okay? Now you can see again, when it de-encapsulated and re-encapsulated the data, all right, it's using a different source MAC address, okay? All right. All right. All right. Let's take a look at the next message. So again, there we go. We have to find some ARP information. Well, we have to find some layer 2 information, and we do that by doing ARP, okay? Address Resolution Protocol. All right. So again, that other frame right there, that actually got dropped by R3. All right, because we didn't know, we had no layer, we didn't have any layer 2 info, okay? Now, R3 and PCC, they're sharing layer 2 information via ARP now, okay? Here comes our next. We have this. We're sending another ICMP message. Okay. So again, our first ICMP message failed. Okay. It didn't go through. It ended up getting dropped. All right. So now we're sending a second ICMP message out. All right. Again, here we go. IP address, source, PCA, destination, PCC now. All right. Here's some Ethernet information. Okay. Is the MAC address for our PCA. Okay, this is the source. All right, the destination. This is PC. The router 1. Routers 1. Okay. All right. Again, layer 3 source PCA, destination PCC. All right. And then take a look at that. So we have, again, we're using, it's when it de-encapsulates and re-encapsulates that data, it's it's putting it in, now this is because it's going over an Ethernet channel, it's putting it into an Ethernet header and trailer, okay? goes over to R3 now. Same thing. Very good. All right. All right, let's go to the book real quick. So again, it's just going over the re-encapsulation, decapsulation. Okay. Connected routes add because the configuration of the IP address. Yep. Static routes, routing protocols. Connected routes added because the configuration of the IP address interface subcommand on the local router. Static routes added because of the configuration of the IP routing global command on the router. Routing protocols adds as a function by default added as a function by configuration of all routers, resulting in the process which routers dynamically tell each other the network so that they learn all the routes. So that's what I did with OSPF. OSPF's a routing protocol, and they used OSPF to pretty much connect me, to advertise all of my available routes. That way, I wouldn't have to statically address these routes in. All right. The second of the three sections discuss several variations of how to configure connected routes, while the next section discusses static routers. Okay. Connected routes in IP address commands. A Cisco router automatically adds a route to a routing table for the subnets connected for each interface, assuming that the following two facts are true. The interface is in the working state. In other words, the interface status is showing interface list, and the line status is up, and protocol status is up. The interface has an IP address assigned through the IP address interface subcommand. Very good. Man, I gotta stand up. Let's stand up. Man, I'm getting aggravated on myself, guys. All right, maybe have some pizza with me. All right, let me stand up, guys. Gotta wake up. All right. Let's dive into things here. Line up. All right. I'm staying up well, man. Sometimes sitting down is no good for me. All right. All right. So here we go. A Cisco router, connected routes, an IP address command. A Cisco router automatically adds a route to its routing table for subnets connected to each interface, assuming that the following two facts are true. The interface is working in the up state. In other words, the interface status in the show interface command lists a line status of up and protocol status up. All right, cool. The interface has an IP address assigned through the IP address interface subcommand. Okay, so you assigned it an actual IP address. Okay, the concept of connected routes is relatively basic. The router of course needs to know the subnet number connected to each of its interfaces, so the router can route packets to that subnet. The router does the math, taking the interface IP address and mask, and calculating the subnet ID. However, the router only needs that route when the interface is up and working. So the router includes a connected route in the routing table only when the interface is working. Okay. All right. And the example shows the connected routes in R1. The first part of the example shows the configuration of the IP addresses, all three R1's interfaces. The end of the example lists the outcome of the output of the show IP route command, which lists the routes for each with C's connected with the routes with list these routes with a C as the route code, meaning connected. All right, come on, Joe. All right. Take a look at that on our end now. All right. A little bit bigger. That way you guys can see it. All right. So, as you can see from right over here, guys, what this is showing us. Grab this one. So we have our connected statuses. I guess don't mind the O's for now. The O's are representing OSPF. And this is what I've talked about the other day with the codes. The show route command actually gives you codes, okay? And we have a couple codes showing on us already. We have obviously the OSPF one, and then we have connected, okay? All right. If we had statically configured these routes, we would have had an S there. If we had used IGRP or EGRP or RIP or something like that, or BGP to dynamically learn these, we would have had, or configured these, we would have had those codes respectively, okay? All right. Again, what this is just mentioning right there. All right, take a moment, look closely at each of the three highlighted routes. in the output of the show IP route. All right. Each list is C in the first column and has text that says directly connected. All right. Both identifying the route as connected to the router. The early part of the route list the matching parameters like subnet ID and mask. As shown in the early examples in the figure, the end of the exam, the end of each list a outgoing interface. Okay, so this right here, guys. So it's just showing us that to reach those particular networks, we have to go out via whatever interface that they're attached to. Okay. All right. Oof, come on, push off, push on. Oh. Oh. All right. All right. Note that the router also automatically produces a different kind of route called local route. The local route defines a router for the one specific IP address configured on the router's interface. Each router has a 32 prefix length, defining a host, which defines the route for which the IP address for example, the local routers 172.16.3.32. Whoa. 76. Oh boy. Guys, I am hurt. I really am. I am trying my best to concentrate. It's like I can't. But life. I hate working overnights, guys. It is messing with me so bad. It really is messing with me. It's like I'm burning the candle on too many ends. For example, the last local route for 172.16.5.1/32 define a route that matches only the IP address for 172.16.5.1. Routers use the local routes that list their own local IP addresses to do more efficiently forward. Yeah. Yeah. For the CCNA, for the CCNA 200-3x1 exam, note that this example of the show IP route command reveals a few of the specific sub items within the exam, with later examples revealing even more details. The section shows details related to the following terms for the exam topics. All right. Shit. Oh boy, I'm a hot mess right now, guys. All right. Ooh. All right. Running protocols codes. The legend at the top of the show IP route output, about 9 lines, list routing protocols. Okay, that's what we took a look at. Okay, this book refers to the codes for connected routes. This book reference the codes for the connected routes as connected routes as C, local as L, static as S, and OSPF. So that's all this book. That's all we have to for the CCNA, I guess, focus on is those 3 codes right there. So, the word prefix is just another word for subnet ID. Okay, mask is each route lists a prefix or subnet ID and the network mask in the prefix format. Okay. The ARP table on a Cisco router. After a router has been added, has added these connected routes. Remember when we were sending those ICMP messages, we didn't have the ARP table. It wasn't populated yet. So after a router has added these connected routes, the routers can route IPv4 packets between the subnets. To do so, the router makes use of its IP ARP table. The IPv4 ARP table lists all the IPv4 addresses and matches MAC addresses of hosts connected to the same subnet as the router. When forwarding packets to host on the same subnet, the router encapsulates the packet with the destination MAC address. All right. As found in the ARP table. That's why we need ARP, okay? Because we need to be able to build that frame, all right? Either that HDLC frame, PPP, or Ethernet frame, okay? If the router wants to forward packets to an IP address on the same subnet as the router, but does not find the ARP table entry for the IP address, the router will use ARP messages to learn the device's MAC address. Okay. R1, the example R1 ARP table, based on the previous example, the output list R1's own ARP address. Okay. Let's take a look at ARP. Okay. Now, here we go. So, what the ARP learned for us is the information that we needed for us to be able to create new Ethernet frames or HDL frames. Okay, so we can encapsulate those packets. Okay, inside of those Ethernet frames there. Okay, and that's why those ARP messages will go out first before our ICMP messages will go out, because we won't be able to successfully create that new frame without having that layer 2 information. Okay, so that's why when we saw those first ICMP messages get dropped, it's because we didn't have the initial layer 2 information that is required to make successful frames or correct frames. All right. All right. So there's the R1's own ARP. Yep. With the age of the minus, meaning that the entry does not time out. Dynamically learned ARP table entries have an upward counter, like the 35-minute value for the ARP table entry. Okay. All right. By default, iOS will timeout, remove an ARP table entry after 240 minutes. All right. Which the entries, when the entries is not in use. Okay. iOS resets the timer to 0 when the ARP table entry is used. Note that to do an experiment in lab, you might want to empty out all dynamic entries or a single entry, so to clear the IP ARP command. All right. So doing that will reset our ARP table, so then we can then see the dynamics of ARP and how they're helping. They're sending out their. So we can see. We'll do that command to clear out the ARP table, to then obviously then see the messages go out. Guys, I am like, whew, I am doing my best, guys, and I am so sorry. This is like day 5 in a row that I am a hot mess trying to do this right now. And I am trying my best to push through this, and I just cannot. This is more for me too, guys. Like, I'm getting mad at myself that I just cannot stay awake. I'm so tired. It's like I just want to fall asleep right now. And I already down the whole craft of coffee. All right, thinking about how R1's routers pack, how router 1 forwarded packets to a host. What's up, A-dubs? Yeah, I'm getting burnt out, man. Stinking overnights, dude. I freaking hate it, dude. It's like I'm all messed up. I'm all messed up. Ever since I started doing it, it's like I can't concentrate anymore. I'm trying my best to just push through it. And it's not doing me any justice, and I know it's not doing the stream any justice. You know? Yeah. How are you today? Happy New Year, by the way, A-dubs. Happy New Year! Right. Exactly. And you're right. You're right. You're absolutely right. You know, sometimes you just need a break. Probably where that's getting towards. But we're trying. We're trying, my brother. Oh, man. All right. All right. Configuring static routes. Let's just try to get through this chapter. All right. Configuring static routes. All routers add connected routes as discussed in the previous section. Then most networks use dynamic routes, routing protocols, to cause each router to learn the rest of the routes in an internal network. Networks use static routes added to a routing tables through a direct configurations, much often the dynamic router, much less often than dynamic routing. However, static routes can be useful at times. They can be useful at times, and they happen to be useful learning tools as well. Thank you, A-dubs. And to you. This next major section in this chapter discusses static routes. So I actually today, because I also have I purchased it a while ago, but it was David Bumble's CCNA, the entire CCNA course that he had on Udemy. Great course, by the way, too. Super long. There's like there's like 700, 800 videos to that one course. It's the complete course. It's the extended long one. And it video by video, he gets nitty, he gets right into every type of subject you can expect to get hit on with the CCNA course. But what I was listening today when I was going through there, because I was listening obviously to the IP routing section, and to really statically route everything would be such a pain in the butt, and things like OSPF and routing, dynamic routing protocols like that. There's just so much useful, and in my opinion, just so much better to just maintain a network than trying to go in there and statically configure the networks. All right, but I mean to learn, obviously it'd probably help us to statically route entire networks, just as a learning tool. But I don't think in reality that would be feasible, just because how much information and how much actually configurations you would end up doing to a network depending on the size of the actual network itself. All right. The static route is considered a network route when the destination lists in the IP route command define a subnet or an entire class A, B, or C network. In contrast, a default route matches all the destination IP addresses, while a host route matches a single IP addresses. That is an address of one host. As an example, a network route. As an example of a network route, shows a subset of the figure used to route this chapter so far. With some unrelated details removed, the figure shows only the details related to the static route of R1 for destination subnet 172.16.2 and the subnet mask of 24, which sits on the far right to create the static network route on R1. R1 will configure the subnet ID mask with either the R1's outgoing interface or Out2's next hop address. So it's just depicting how the route, like, it's just saying, okay, if I need to get to this subnet, then I have to go through X subnet, which is like next, like, if this subnet, it's like, let me just, probably easier for me to illustrate it. So, 7.2, 16, 4, 1, 7, 2, 7.2, 16, 2, 9. So if I needed to get to, if I got a packet that's destined for 172.16.9, I would have to have static routes configured to tell me that to get to 172.16.9, my next hop would be 172.16.4.2. Off of 172.16.4.2, that lives the 172.16.2.9 network, and that's what that's saying right there. And that to statically configure all that would be kind of a pain in the butt. Took us, instead of having like OSPF dynamically advertise that. So OSPF is sending out those hello OSPF messages, all right, advertising routes to routers that it's connected to. So this route, this OSPF knows within the 172.16.0.0 network, it should go out and everything within this network range, it should go out and try to find routers connected to that same network, and then see if those routers have any information to relay back to the other routers to advertise routes. So what we did in that lab on packet tracer is I just enabled OSPF for the 172.16 network, all right, and I did it for the whole 172.16 network in entirety. So these routers are relaying, saying, okay, well, I have this subnet, and then I have this one, and then I have this one. So all of these routers are sharing all that and advertising that information. Again, making routing a lot easier, so you don't have to go back and then statically do this all statically on your own. All right. And this is just an excerpt on how you would configure that. So on a serial route, and this is where it's stating on a serial route, you wouldn't per se add the next hop like router. You would just put the actual interface that route is connected to. So 172.16.2, that network right there resides off of the serial 0-0-0. So as in the so IP route 172.16.2, this network lives off of this interface. All right, so if I get anything destined for this network, I know that I just have to send it out of that interface and I can get to that network, okay? We're on an Ethernet, so the Ethernet, so this cloud right here, this is representing Ethernet, and obviously with this squiggly line, the lightning bolt there, that's representing serial. All right, on Ethernet though, you'd want to assign an IP address. So on this interface, on the gigabit 0-0, on the router 3's interface, it has a IP address of 172.16.5.3, and if I get anything packets destined for the 172.16.5 network, I know that I just need to send it what's connected to me local. All right, so this is connected though, okay? So since that's connected, I must have an interface right here that's saying there's a 172.16.5. So I must have a 172.16.5 on my interface here. Let it be 1, which I'm pretty sure that's represented because that's what we recreated in Cisco Packet Tracer. All right, so I know that that's connected to me. So I just need to send it to that next hop router here, and that'll get me to the 172.16.3 network there. Okay. All right. The two examples commands show the two different styles of forwarding instructions. The first command shows subnet 172.16 with the mask 255.255.255.0, which sits on a LAN near router 2. The same first command lists the serial 0-0-0 interface as the outgoing. This route basically states to send packets to the subnet off the router, all right, and then send them out my local serial interface. The second route has the same kind of logic, except for using different forwarding instructions. Instead of referencing R1's outgoing interface, it instead lists the neighboring router's IP address in the wide area network link as the next hop router. This route basically says this packet to send this packet to the subnet off of R3 router R3 and send them to R3 specifically R3's WAN IP address next. Oh boy. Come on, we can make it. The route created by the two IP address route commands actually looks a little different in the routing table compared to each other. Both are static. However, the route that lists the outgoing interface configuration is also noted as a connected network. This is just a quirk of the output of the show IP. Yeah, so even though it says connected, I guess that's just a quirk in it. List the two IP routes using the show IP route static command. This command lists details of static routes only, but it also lists a few static IP average IPv4 routes. For example, the example. Again, I hate the way some of these chapters are written. It makes me stumble over my own words. Shows two lines for the two static routes configured, but static state this router has a route for 8 subnets. It's like I'm reading a Dr. Seuss book sometimes. iOS adds and removes these static routes dynamically over time based on whether the outgoing interface is working. For example, in the case the router's serial 0.0 interface fails, R1 removes the static route for 172.16.2 from the IPv4 routing table. Later, when the interface comes back up, iOS adds the route back to the routing table. Note that most sites use dynamic routing protocols to learn all routes to remote subnets rather than static routes. However, when not using dynamic routing protocol, the engineer would need to configure static routes to each subnet on each router. For example, if the router only had the configuration shows in the example so far, PCA would not be able to receive packets back from PCB because our router R2 does not have the route for PCA subnet. R2 would need static routes for the other subnets. All right. Finally, note that the static routes that will send packets out the Ethernet interface over the LAN or WAN should use the next hop IP address option on the IP address command as shown. Routers expect their Ethernet interfaces to be able to reach each other over the IP addressing. In the connected subnet, referencing the next hop router identifies the specific device in the connected subnet, while referencing the local router's outgoing interface does not identify the specific neighboring router. Static host routes. Earlier in the chapter, define a host of routes to a single host. To configure each static route, the IP route command uses a IP address plus mask of 255.255.255, so that the matching logic just then adds one address. An engineer might use hosts to direct packets sent to one host to another over one path, with all other traffic in that host subnet over that path. For instance, you could define these two static routes for the subnet 10.1.1.0 and host 10.1.1.9. The two different network addresses as follows. Holy guacamole, Joe. All right. Where are we at? All right, guys. I'm gonna take actually a break for a little bit. I'll be back on. Okay, I gotta maybe wake up somehow. So let me take a break. I'll be back on. Like I said, I'm not working tonight. So let me just take a little bit of a break, and then I'll be back on later on tonight. If you're still up, I'll be happy if you guys join me. If not, you can catch the stream later. Happy New Year to everybody again. But again, I just need to take a quick little break. So again, I can get my mind, my mind right. So I apologize, but I just need to take a break, guys. All right. So again, I'll be back on. I'll be back on it probably within an hour or so, guys. I just need an hour to get my mind right. So without getting too much into everything, guys,